it's very new, and there's actually a couple pieces that I'm still missing, but I thought it might be a nice, I don't know, fun thing to talk about.
Touch.
You can touch it, yeah, you can touch it. Just don't do anything beyond touch it. So this is our the sensor that we've attached, that we're attaching to it, right? So obviously you need the platform, right? Remember we talked about whether it's a plane, whether it's some kind of a satellite, there's the actual platform, and then there's the sensor attached to it. Sometimes we can attach multiple sensors, sometimes not. So in this case, this is great. I don't have the batteries on here, but we can attach what they call the payload on the bottom, and obviously you need a drone or a platform that's going to be able to carry your payload. That's it's going to be a problem, right? If that's not the case. Daniel.
How much does one of these cost?
Good question. It varies a lot. There's a lot of money sitting on the table right now.
Yeah.
A lot of money sitting on the table right now. Just this is a lot of money.
Just the camera?
Yeah, this is yeah, and so this camera. Why I'm so excited about this? So it's a. What's that?
I said I can feel your nerves.
Yeah, very much so. When you're in the field, you get real nervous about these kinds of things. So this has, well, it essentially has 6 bands because there's a panchromatic band. Does everyone remember what the panchromatic band does, or what it covers? Everything. Yeah, exactly. Everything. Sometimes we think it's like, oh, it's just like a grayscale thing. It more or less looks like if you just took a regular image and put it in grayscale, but there are some subtleties. But yeah, it actually kind of goes across the whole way. But this is beyond that. This has 5 bands. So it's got blue, green, a red, and a near infrared. But then it also has a red edge band, which I'm really excited about. And we'll get more at that in just a second. So so a couple things. Spatial resolution, well, it's going to depend how high you fly, right? But this sensor, it's pretty slick. If you fly at a fairly standard altitude above vegetation, above trees, we can get about 8 centimeters of our pixels, which is really, really fine. Almost, depending on what you're looking at, could almost like drown you out in data, so to speak. Does anyone remember when I talked about, like, I'm not anti great spatial resolution by any stretch, but spatial resolution is great. But is it as helpful as temporal resolution? Does anyone want to comment on that?
Depends what your question is.
Ooh, yes. Yes, I like that answer. Did anybody hear what Mike said? Depends what your question is. So if I only need to get a single shot of something, great. We might want the highest resolution we can get. If we want to get repeat coverage, well, if it's right down the street, great. We can probably get repeat coverage depending on the weather. If it's on the other side of the world, it's going to be a little bit harder to do. One of the things that we do that's very common these days in remote sensing is what we call scaling up. So I do this a lot where I measure stuff on the ground that has nothing to do with remote sensing or cameras or anything like that. Measuring trees, measuring canopy cover, things of that nature. And then I scale that up in a statistical model, just saying, like, what does the satellite say? Like for example, maybe the near infrared. If I have higher canopy cover, I'm going to have a higher amount in the near infrared. And I'm going to build a statistical model to kind of figure that out. Where am I going with this? I feel like I had a point. Damn. I was crushing it and I forgot.
Does it fly above the clouds sometimes?
Well, in theory it can, but that's a big no-no by the FAA. So
Yeah, because that's what planes for.
yes, yeah. So it gets really complex really quick, and it's very much described as like the Wild West because there's been so much change in the drone world. For example, if your drone is below, I think it's like 250 grams. There's some crazy small drones that they make these days. You don't need a license for that. If it's greater than 55 pounds, you need a very, very special license for that. 55 pounds is a lot of weight. I mean, even this thing, like, it's actually, and we don't even have the batteries on it or the payload. It's a lot heavier than one might imagine, and it's because we need to be able to carry this sensor.
How far can it get out?
Good question. It depends on it depends on basically the receiver that you have. But again, if you're not breaking FAA laws, you have to more or less have it in sight. And I know and that doesn't happen all the time. We know that, right? We know that. Years ago, I was backcountry skiing in Colorado in a wilderness area. For a lot of reasons, one of why I'm skiing in the backcountry is because I want to be in the backcountry, right? I don't want to get there by a lift with a couple of friends, and we hear something weird, and it's a freaking drone, and no one in sight, like no clue where someone is, and they're presumably trying to get footage of this other party that is talking some sweet jobs.
We have some sites on national wildlife areas in Ohio here, and we have a drone team that comes in and surveys our wetlands, and they were told by the National Wildlife Area, whom we have sites on, like built with H2 Ohio, they were like, yeah, you can fly and tape and record all these sites or do whatever sensing you need to do, but you can't fly it from our territory. You have to stand on the road, deploy it, and then have it come back.
Yeah, and I get that to some degree. So, NPS is very similar. But yeah, a lot of times you have to get permission. There's also airspace, and there's all kinds of different types of airspace. And so, you know, if you're flying a drone anywhere near like a commercial airport, very, very much a no-no. And you can, whereas if it's an airport that is, you know, very small airport, far away, you can get permission, and you'll likely get it granted. If you try to get permission from, you know, Cleveland's International Airport, you're not going to get permission to do that kind of thing. But the big thing is it is changing so much, and some of you may have heard me say this before. There's a big part of me that like I wanted no part of this because there's a lot of things to worry about, right? You're gonna hit something, you gotta. What if the thing fails and what they call a flyaway? Ooh, that's pretty bad. But the kind of data that we can get is just kind of amazing with this scale of observation. So I want to go back to this sensor. We talk about the red edge. So is there anyone here, the intrepid student, that would like to draw an approximate spectral curve of like typical vegetation for us on the board? Just give it a shot. You want to give it a shot, Sarah? All right. Let's what you got? I don't know whose drawings those are.
Yeah, I like the turtle.
They're pretty
Yeah.
nice. Those are mine, and they're pretty bad. So I know that. Okay.
This is like
Yeah, just give it perfect. Just give us the rough.
all this is blue, green, it's red. That's a little far out, but
What do people think of Sarah's curve?
Yeah.
It's good. Yeah, nice job, Sarah. Good job. Okay, so a couple things. What Sarah just did, everyone should make sure you can do that. Keep in mind, you know, she's not haggling of like, oh, how far do I have to go into the near infrared or anything like that. That's okay. Also, keep in mind, there's no specifics here in terms of the different spectral range. Although some general ones are good to know, although I don't want you to necessarily do that. Just throwing it out there for the exam. Does anyone know roughly what the blue range might be? Off the top of your head?
Is that around 300?
Is there something else? 400.
Okay.
400 to 5, I mean, roughly 4 to 5.
Okay.
5 to 6, 6 to 7, beyond 7. And different sensors, like if you look at Landsat versus some other satellite, they'll have slight differences in the red band as this, but that's the general idea there. You want to know those general amounts as well with respect to that. Okay, so a couple things. I'm actually going to add to Sarah's very nice. Good job, Sarah. Out here. So this is the near infrared. This is the shortwave infrared, which we haven't really gotten into yet, but we will coming down the line. So a couple things. So this is a typical. What kind of plant would you say this is there? What are you drawing here?
some sort of tree.
I'll be very facetious because this is a general curve. Would this look different if it was something else some other type of species?
Probably.
Probably, but it might be very similar in certain places. And I can guarantee, if the leaves look the same shade of green, those curves are going to be very identical, nearly identical right here. But they might look a little bit different in near infrared or something like that. So a couple things. We can look at these different curves at one point in time if we've got different vegetation types. They're all going to resemble each other compared to like water or bare soil, but there might be some subtle differences. Or again, we can look at the same piece of ground at different points in time if something changed.
So those differences, those subtle differences be determined by, you know, the changes in the season, like depending on how that goes.
Absolutely, absolutely. If we threw a satellite out there on a giant oak tree right now, do you think we would see this curve? No. It would look definitely different. It might look a little bit more similar if we looked at a conifer forest, right? Because those things are still there. They're not photosynthesizing because they're limited by temperature, but they can retain that tissue, and so it's still reflecting that same level. But yeah, basically what we see, if we track the same piece of ground, if we track front campus, it's going to be pretty similar. What's driving it right now are going to be differences in snow cover, right? It's snow and non-cover. But as things, right, it's a little chilly this morning, a little chilly this week, but hopefully in a couple of months we're going to get some warmth coming back, and we get bud break. And when bud break happens, right, that's when we start to, this curve is going to start to take shape at that time. And then it's going to be somewhat maintained through the growing season. And then what's going to happen in the fall, that curve is going to start to break down again as well. And to get really specific, right, where we live in Ohio, in my opinion, one of the best things about Ohio are the falls, right? Pretty great fall. I love the West, and I love aspen trees. It's one of the things I study. There's not a ton of color when it comes to trees out west. The East, you can't beat it. What's the big thing? What's so great about leaf season here is it doesn't happen in one day, and it doesn't all happen at the same time. Why? Because we've got different species that are changing at different times, and there's also microsite conditions, right, where they're going to change a little bit higher in elevation or more exposure, soil moisture, things like that. Same thing here, as that basically the chlorophyll process starts to break down, we'll start to see some of these subtle differences at that point in time. Okay, so last thing I want to talk about here is, so this curve is continuous, right?
Yeah.
This curve is continuous. Digital sensors can't really see continuous, right? Because we've got to set that to channels. So if we think about the different channels that we have here, blue.
Are the channels now just the bands, or?
Yeah, sorry, I shouldn't say that. Yeah, I should have said bands. When I say channels, I'm thinking more of the three channels in our eyes that we see in, but bands can be way more than that.
Gotcha.
Yeah, so look something like this. Let's think about the air photo from lab last week, right? So we had 4 bands. We had the near infrared band, and you know, in the MIG camera, it might cover those wavelengths, the red, the green, and the blue. So remember, this thing I said, it's got an additional band called the red edge. Does anyone remember? We only probably talked about it very briefly. Does anyone remember what the red edge is, or can they describe the red edge? Anyone? Maybe I'm making this up. Maybe we did not talk about it.
I don't remember
did.
talking
Okay.
about this.
The red edge is basically this.
You mean infrared?
No, it's different.
So it's this idea here that we've got absorption in the red band. So we've got absorption in the blue, get this little hump in the green because we get more reflectance there, but then we get absorption again in the red, but then the reflectance skyrockets up to the near infrared. So the red edge, and it varies depending on the sensor, the red edge is this middle area there. The idea here is if you've got that, the slope of that red edge can change if you've got different vegetation types, or if you've got basically different conditions of the same vegetation type, and it's really, really sensitive, right? So these bands tend to be about this wide, but the red edge band, they're really, really narrow, and it's to capture those subtle differences. It's true, like depending on what it is, it could be very different. Just the range you're having to get at is the fulcrum, so it's not actually changing. But that is why this camera, what I'm really excited about with this sensor, is that it also has this red edge band, which will be really, really sensitive to those differences there. So if you're looking at, say, different species composition, Hannah in there this summer, that's what she's going to be doing in northern New Mexico, is going to be looking at basically resprouting deciduous, woody deciduous shrubs. Why are they coming back? They're coming back post-fire. But we've got different, a couple different vegetation types. We don't know this because no one's really looked at this yet. There's a good chance that they look pretty much the same here, 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 and back here, but they might look different there. So that's a sort of big thing that we're looking into. The other thing I want to talk about is, and we'll get much more into this when we talk remote sensing of vegetation, but is in the shortwave infrared. That's where we start to see some differences in terms of water content, right? All vegetation has water in it, but we see different levels of it in different types of vegetation, and also with condition, right? That's a big deal. And the final thing out in the shortwave infrared is when we have differences in basically the cellular level structure of leaves, it's kind of crazy, differences are manifested in the shortwave infrared bands. Because you just get these subtle slight tweaks of differences there. We're able to pick up on those differences. Can we see those right now? Exactly, right? We're really far from the visible portion of the magnetic spectrum. We're way out here. And we'll start seeing some of those come into play in future lectures. Okay, that concludes our field trip for this time. Any questions that anyone has that I may or may not be able to answer, since this is still very new?
So you said that like the different leaves have different shortwave infrared signatures. Is there like a standardized like measurement way to do that, and then like almost like data bank of all their different values?
There is, and some people do that sort of thing. So Dr. Ortiz, that Colton works with, he has what's called a spectrometer, right? Have you gotten to play with it? Spectrometer is really cool because you can basically think high summer. You can go out there to an oak leaf on a tree, or maybe one you just pulled off before it starts to senesce, and you clamp it on there, and you're going to get continuous readings all the way across that spectrum. So then if you take that and put it on, a different species of oak or a maple tree or something like that, you can actually look for those subtle differences. But yeah, then what people do is there are things called spectral libraries where people put together these, you basically need a spectrometer to be able to do that. A lot of geologists use it for different types of earth minerals that you can see with respect to multispectral remote sensing. But yeah, they're called spectral libraries. And that's very much a thing. It can be hard to work with those depending on the scale of your data, because Landsat, that we're going to get much more into. Does anybody remember the size of a Landsat pixel?
30 meters?
30 meters. Anybody remember the size put it on a sports field, the analogy? Baseball infield, yeah. About a baseball infield. So you can imagine, right? Think about that baseball infield anywhere on campus. If it's in the middle of a big field, like one of the commons, yeah, it's all going to be grass. Or if it's in the middle of the forest. But sometimes if it's like, half tree, half grass, what happens? Well, it's an amalgamation of those reflectance values being evened out within that pixel. So it's something called spectral mixing. People do try to get at using spectral libraries to what they call unmix a pixel. And there's some of it works really well, some of it doesn't. So yeah, it's a good question. Yeah. But it's hard to get at those spectral libraries at these giant,
Yeah, that makes sense.
broad landscapes. Yeah. Any other questions?